All right, we're back with part two, and as we mentioned, I mentioned in part at the end of part one, there's actually three methods for calculating or estimating the instantaneous rate of change. The first one was the one that was quite natural, is where we thought of p getting closer and closer to q from the left, but we could have if we wanted to. Let me see if I can do this. I could have grabbed p and put p on the right and snuck up on it this way. And I get closer and closer to my slope of 4.5 as p gets closer and closer to q from the right. It's like the interval is after q. And that's the second technique. It's called a following method. And this is the idea of p sneaking up on q from the right. Well, what would our intervals look like then? Because we're still just going to calculate the Iroc over smaller and smaller intervals. And the idea is we start big and go small so we can find a pattern, right? So if we still know that Q is one of our points, but it's going to be the start of our interval, right? I've got this time P is over here, and I'm going to drag it back. So that means Q is the first one. And maybe we'll start with a delta x of 1 and use the same pattern. So where would P be? P would be at 2, wouldn't it? And then our Iroc is still y2 minus y1 over x2 minus x1, or f at 2 minus f at 1 over 2 minus 1. Well, f at 2 is, and this one I can do in my head, right? Just try and stay away from, I'm a little calculator shy now. That's 4 plus 4 is 8. So I get 8 minus 3 over 1, which is an estimate of 5. Okay, and not a very good estimate because our delta x is. And now that we sort of get the picture, I can go a little bit quicker here, and I want this p-value to get closer and closer back towards q. So, I might try 1.5 and then do that calculation. And I'm going to actually try and put this whole thing into my calculator now. And my delta x is 1.5 subtract 1, or 0.5. And I'm going to actually just do that on my calculator, or try to atone for this. Bracket, and then I've got my 1.5 squared plus 2 times 1.5. I'm putting that in brackets just so I know what values I have to change when I redo my calculation. Subtract 3, that's the f at 1 that we know, divided by, and this is going to be my, I suppose I could put in my x2, 1.5 subtract 1, the q value is 1, and then get my new value, which is 4.5. And I'm expecting, well, I already know the answer is 4, but I'm expecting this to get closer and closer to 4. What would be the next point? Q starts at 1, and now I want this value to get even closer to Q with the value of a delta x value of 0.1. This is going to be 1.1, right? And then I get my value even closer. And now notice that I'm getting a little bit lazy, but I've shown the pattern. And I'm going to use my calculator and just change the 1.5 to 1.1. And I get a value that's even closer to 4, right? 4. What would be the next one? That's even closer, 1.01. My delta x is only 0.01, and I get a value of 4.01. And you're going to have to trust me on that one. And notice, same conclusion. All right, so makes sense. Preceding and following, I should still get the same estimate. What's the third one? You said there were three. What's the third one? Well, the third one's actually pretty neat. It's called the centered method. And you're going to like this one. Well, actually, you won't like it too much. What's nice about this one is for this example, it works perfectly right off. And instead of having P get closer to Q, essentially what I'm doing is I'm having Q in the middle of some interval that I choose. I'm going to pick a little bit of on either side where Q is in the middle, and I'm going to go the same distance on either side, so it's going to be centered, if you understand what I'm talking about. So the idea, my interval, and then the Iroc. So if Q is in the middle of my interval, and I want to go a little bit on either side, for instance, that might be where I start, from 0 to 2, because notice Q is right in the middle there. And then if I do my Iroc calculation over that interval, and this is what's kind of neat about this, f at 2 is 8, subtract 0 over 2. It gives me what we call the right answer straight off. This one does, at least. And in fact, we can't get any better than perfect. Even if I shrink my interval, what would be the next interval that when we pinch closer to Q? Remember, Q's got to be right in the middle. What would be closer? Well, I could have 0.5 to 1.5. And in fact, what's weird about this one, you bash that into your calculator, and you still get 4. And that's, by the way, this is just coincidence. It's not always perfect, the centered method. And then what would be the next best interval? Well, I'm pinching closer and closer, to Q in the middle. Q is always in the center of my interval. And so on, and I still get 4. What would be the next interval that's even closer? I'd get 0. A little bit to the left, and a little bit, a little bit to the right, and I still get 4. So, well, why wouldn't I just use the centered method all the time? Well, this calculation actually is a big, big pain. Think about it. I mean, we had this 3 represented a calculation that was perfect. I would have to have an expression like this, subtract another expression like this, over, and these decimals are terrible. So this calculation is no fun at all. And if you try that on your own, you'll see that we've got decimals on both sides rather than having that number, the 3 and the 1 in this case. That's absolutely perfect. And whether we used the preceding or the following, we always had one of the values that was exactly right on, even though this estimate went closer pretty quickly. In the homework, when they ask you to use all 3, you use all 3. Okay? If they asked you just to use a preceding method, use a preceding method. In long term, what we're going to do is, after today's homework, we're going to just be clever. We're going to use either a preceding and a following method and just choose our points very close together. Just sort of skip to the one where, yeah, I think I can figure out that that's supposed to be 4, even though I'm a little bit off. After today, but today you actually have to go through all these calculations. Example 2, I'm going to dump this on you folks. You're going to read this example, which is exactly like this one. The whole idea is, how do I calculate the instantaneous rate of change if I don't have an equation to substitute into? What happens if I want to find the instantaneous rate of change at a particular point when I'm given a table? Well, you read that example. You can try my example of Ferdistan, and then I'll post my solution on Facebook to see if you got the same thing. But this is for you to do. Okay, so read that example, and you can try my second example, and then we're into the homework. Okay, there's only a few. Oh, and there's a handout too. This is a huge day. Big day today is you'll have to do this handout in class as well as the FAQ. Big day. Wow. But that's it.